Hello, this is Ching Chao Huang from a Tech Corporation based in the Silicon Valley, San Jose, California. Welcome to In-Situ De-embedding webinar. Now, we are going to have quite a few people today, and today's presentation can be found at this link, or you can go to our website homepage and click similar link. Now, let me start by saying fixture removal has come a long way. Not too long ago, people have been using port extension followed by TRL and 2x through the embedding. About 8-9 years ago, we first introduced In-Situ De-embedding, or ISD. Now people call ISD's technique as impedance corrected embedding. Basically, it can adjust for impedance variation between fixture and calibration structure. So it helps you remove causality error in DUT, device under test. As the requirements grew, so did ISD. So over the years, we have included many functionalities. Now we can take care of arbitrary endport de-embedding, narrowband de-embedding. We can de-embed imports from imports. N and M can be arbitrary. We can de-embed vias, sockets, or package. Of course, we can de-embed pair-to-pair crosstalk and mode conversion. Now, when fixture has very large impedance discontinuities, or the fixture is very large compared to DUT, this is the kind of problems that could not be done before, and now we can handle that very easily. So here's the outline for today's talk. We are going to talk about causality, what's In-Situ De-embedding, ISD, and we'll compare ISD results with simulation and other tools, how non-causal de-embedding affects connector compliance testing. We are going to talk about how to extract accurate PCB trace attenuation that's free of spikes and glitches. And based on the results, we can then extract PCB's Dkdf and roughness very accurately. We are also going to talk about Pcie 5.0 spec, CCICN, etc., etc. At the end, we are going to do a demo and open the floor up for Q&A. So people use VNA, or Vector Network Analyzer, to measure S parameters. S parameters are complex numbers for an N by N matrix. For an import device, S parameter is an N by N matrix. Now, S parameters are recorded in touchstone files or SMP file. Basically, it's an ASCII file, or you can say text file. So for every frequency, you have S parameters in complex number, either in dB, phase angle, or real part, imaginary part, etc. And you have reference impedance, typically in 50 ohms. So now let's talk about causality. Causality relates cause and effect. So in an electrical world, we basically said, yeah, we cannot get something from nothing, or before the input signal arrives, we cannot have output signals. So why are we talking about causality, right? And now when we look at S parameters, they are just a whole bunch of numbers. And so it's hard to tell whether it's right or wrong. So very easily, if we want to tell whether S parameters are causal or not, we can convert them into TDR or TDT. The response before time zero or after DUT are non-causal, right? So in this graph here, we can see that there's some response before time zero and also after DUT. Many people began to realize causality problem is a problem. It caused a lot of issues, and they began to talk about response before time zero. But we want to point out that response after DUT is also something we want to be careful about. Some people just try to zero out response before time zero and say, oh, it looks causal. But in effect, they cannot take care of causality problem after DUT. So you want to point out that, yeah, when we look at causality issues, we want to look at before and also after DUT. In frequency domain, you can look at the phase angles. When they are counterclockwise, it's non-causal, but beware that this is a necessary but not sufficient condition. In many cases, the phase angle look perfectly clockwise, but actually they are non-causal. And one typical example is from port extension. Yeah. The results you get from port extension basically just shift the TDR or TDT waveform, the entire waveform to the left, and the phase angles are not really changed. They are offset by certain degrees, and so they are clockwise in phase angle, but actually they are non-causal. So why does S parameter violate causality? And we talk about measurement error due to de-embedding primarily, simulation error, right? When you enter constant dk and df into a simulation tool, it certainly is going to give you non-causal results. And also finite bandwidth of S parameters can lead to non-causality also. Because based on Kramer's chronic relation, right, the real part and imaginary part of an analytic function should be related to each other through Hilbert transform. And this Hilbert transform is integrated to infinite frequency. So when we truncate it, like in a touchstone file, then we begin to get causality problem. But of course, when the energy is small at high frequency, and this non-causality issue is not, well, too severe, then we can say, yeah, that's good enough, we let it go. But of course, in this presentation here, we are going to focus on the causality issue due to measurement error, especially from the embedding. Now, what is the embedding, right? To remove the effect of fixture and extract the S parameter or DUT, that process is called the embedding. Typically, we cannot measure a DUT directly, so we have to mount it on a fixture, and that process of removing the fixture effect, right, is called the embedding. Now, why do most embedding tools give causality error? in the past many years, people have been using a separate calibration structures, or you can say test coupons, to do the embedding. The process was that you derive all the necessary parameter from this separate test coupon and then apply it directly to do the embedding, assuming the fixture B here is identical to the test coupon C, and when there's difference, all that error remain, and that error shows up before DUT and also after DUT. Now in S parameter, in frequency domain, obviously it's hard to tell, but if you launch a waveform in time domain, you are certainly going to hit this causality error first before DUT, and also you are going to see this causality error after DUT. Right? So in the past, people use test coupons directly to do the embedding, and then when B and C are not the same, which occur 99% of the times, then you are going to get this error. Now, we introduced In-Situ De-embedding to address this impedance variation between a fixture and the test coupon. It's very easy to use, 1, 2, 3, 4, and that's it. The first step, you bring in the touchstone file for your test coupon, whether the test coupon is in 2x through or 1x open, 1x short, etc. You bring in that test coupon touchstone file. The second step, you bring in the touchstone file for the entire fixture plus dot. The third step, you can click Auto to select the port sequence automatically. It's going to give you a summary of the port connection and frequency number, etc. And then it's going to set the port sequence automatically. And if it appears something different from what you thought it should be, then you can go back and check your data or reorder your port sequence, etc. And then step 4, you just click Run, and then it creates the embedding files by default from the left side and also from the right side, and then the DUT file by itself. So fundamentally, ISD uses test coupon, right, as a reference, and it doesn't apply that test coupon directly for the embedding. It only uses the test coupon as a reference, and then it embeds the fixture's actual impedance through numerical optimization. We'll show that in more details later. And other tools use test coupon directly for the embedding. And then, as we said before, it's going to give you that kind of causality error when test coupon and the fixture have different impedance. So in the end, ISD can address impedance variation between test coupon and the actual fixture through software instead of hardware, instead of tightening the hardware. And in the end, it helps you improve the embedding accuracy and reduce the hardware cost. So let's talk about the test coupon. It can be in many different forms. 2x through is typically used. 2x through is 2 times the lead-ins or 2 times the lead-outs. It's not just to short the DUT, right? And so that the left side is connected to the right side. In case the left side and the right side, or the lead-ins and lead-outs are different, then we want to prepare 2 sets of 2x throughs, one for the left side, one for the right side. But basically 2x through means 2 times the lead-ins or 2 times the lead-outs. Right? And 1x open or 1x short. Now, when 2x through is not possible, then we use 1x open or 1x short. Basically, we want to open up DUT, open up the end of this lead-ins or lead-outs, and also for 1x short, you want to short everything at the end of the lead-in or lead-outs. Now, if you have both 1x open and 1x short available, you can actually equate them to effective 2x through. The process is very simple and is covered by our patent. 1x open is sort of similar to the PMC boundary condition, perfect magnetic conductor boundary condition. 1x short is very similar to PEC or perfect electric conductor boundary condition. So you can combine them into a structure with a symmetry plane right in the middle of this symmetric structure, right? And the process is very simple. So you can combine 1x open and 1x short into an effective 2x through, and then we can apply the existing algorithm to do the embedding, etc., etc. So here's a quick list of Isd advantages. Now, accuracy compared to others, right? Obviously much more accurate. Cost saving, it can help you save money because now you only need to use inexpensive test fixture. You don't have to tighten up the impedance variation using very expensive material. And also for compliance testing, it can help you save money by avoiding components, right, from being thrown away by mistake. Yeah, we'll show one example later. And technology, yeah, it uses impedance corrected 2x through or 1x open short to do the embedding. And in terms of capabilities, yeah, we can embed arbitrary number of ports, 1 port, 2 ports, 99 ports, not a problem. We can embed N ports from M port devices. This is actually important for RF or MEMS device because some devices have 5 ports and they want to embed 2 ports from the left side first and then 3 ports from the right side next. So yeah, the ability to embed N ports from M port device is actually very important for lots of active device manufacturers. And yeah, we are the only one that can embed mode conversion. And we can even use a single line to embed crosstalk. We'll get into that later also. And we can embed longer or shorter than existing test coupons, automatic skew, yeah, etc., etc. There's a more detailed list in this link here. Now, why Isd is more accurate and save money? Compared to TRL, for example, yeah, obviously we only need to use a very simple 2x through trace, for example. And technology-wise, yeah, TRL is still assuming every test coupon has exactly the same impedance. Obviously, that's not achievable when you have so many test coupons, right? How can you guarantee every test coupon has identical impedance at every picosecond, every location along the way? And so in the end, yeah, Isd can let you use inexpensive material. It can help you save money. Now here's one example, mezzanine connector, comparing Isd with TRL, right? The DUT is this mezzanine connector sandwiched between 2 boards here. And we want to embed the boards from the top and also from the bottom, or we can call it from the left and from the right. Now here's a quick comparison, yeah. So if you compare Isd with TRL, one conspicuous difference is that TRL gives you a lot more repos. And ISD gives you smoother curves. And then you say, well, how can we know which one is correct? So you convert them into TDR waveform. And indeed, yeah, for TIL results, you see non-causal response before time zero and a little bit after DUT, which is harder to tell. And if we zoom in, you see, yeah, causality errors from TIL in every term, not just return loss, but also insertion loss, next and fixed. Now, how did the ISD do it? Basically, the blue curve here is the fixture plus DUT, single-ended impedance. And yeah, single-ended impedance is very high here for DUT, although it's tightly coupled. So the differential impedance will be close to 100 ohm. And now 2x through impedance is close to 50 ohm. And within 3% or 5%, right, impedance tolerance compared to the fixture, we say, well, we don't use a 2x through impedance to do the embedding. We will still follow the fixture's impedance to do the embedding, which we can tell from the TDR waveform. And then, of course, after the embedding, we don't have causality error. Now, in differential response, we can do the same thing, right? For ISD, we'll just follow the differential impedance for the fixture, and we use that to do the embedding. So in the end, the results are smooth, but for TRL, you again gets a lot of ripples. And by now we know so many ripples in a small fixture or small DUT is not real, right? These are actually non-causal ripples, as we call it. And when we convert them into TDR waveform, we can see that TIL results actually have a huge causality error before time zero and also after DUT, as you can tell now. Here's an example for the embedding from a large board. And for the sake of time, I'll just go through these slides very quickly. And because we want to save time for demo and the Q&A. And so for large board, yeah, again, we want to extract this DUT, small mezzanine connector. And if you use other tools, after the embedding, the results are even worse than before the embedding, right? The blue curve is before the embedding, the red curve is after the embedding using other tool. We call it tool A here, a very famous commercial tool in red curve here. And if you use ISD, you'll get this black curve, yeah, nice and smooth response, and it's easier for correlation. So how did we do it? Yeah, again, if you look at the 2x through, right, versus the fixture impedance, that variation is certainly within 3%, 5%. But when the fixture is so large compared to DUT, all that little difference are pile up together into a DUT, and the results, if you use the other tools or the traditional method, it's going to be, yeah, obviously very terrible. And for ISD, we just follow the fixture impedance, and then we use that to embed. So the results are perfectly causal. And then, yeah, here's a comparison in TDR. Now for USB Type-C connector, right, again, compare with tool A. Yeah, we can see that for that little DUT, using tool A, you get a lot of ripples. And if you use ISD, you get smoother curve. And in TDR waveform, you can see that again, if you use other tool, you get the causality error before and after DUT. Now, the embedding can certainly affect compliance testing, right? So In this case, it shows that if you use tool A, it actually is going to conclude this component fails the spec due to this embedding error. But if you use ISD, it's going to save the component by saying that this component passes the spec. So this is very important for compliance testing, and ISD can certainly help you save money there too. Now here's a resonator example. We compare ISD with tool A and also simulation. Right. So the DUT is this piece here. And you can see that if you use tool A, the results basically cannot be correlated with simulation. It's all over the place. And if you use ISD, it correlates so well. So now you can talk about design improvement, and et cetera, et cetera. Now here's another example, IEEE P370, or now people call it IEEE 370 plug and play kit. To mimic the real world situation, we are using a 45 ohm 2x through to embed 50 ohm fixture. If you use tool A, basically, it doesn't correlate with the direct measurement, right? The plug and play kit allows you to measure each individual piece directly. And if you use ISD, it correlates so well. So especially for return loss, if you see so much difference, right, between after the embedding, right, compared to the true results, that results certainly cannot be used for Dkdf and surface roughness extraction later, right? So if you want to talk about Dkdf surface roughness extraction, you had better make sure that you have every term correct, after the embedding, insertion loss, return loss, etc. Again, how do we do it? Even if we are using 45 ohm 2x through to the embed 50 ohm fixture, right? We don't use a 2x through directly. Instead, we follow the fixture impedance to do that kind of embedding. Now let's talk about ISD compared to delta L. Delta L is really eigenvalue solution. Basically, you embed a short trace from a long trace, and then you want to get a trace-only attenuation. Eigenvalue solution, or delta L, is really not the embedding. It's just a formula to compute trace attenuation. And the process is quite simple. You convert S parameter into T parameter, and you assume the left side and left sides between the short and long traces are identical, and the right side and right sides are identical. And then you assume after the removing this or the embedding, the launch structures, the DUT itself is a uniform transmission line, and that trace-only attenuation can then be written in one equation here. So the process is actually quite simple. But of course, there are two big assumptions here, right? And if they are not met, these requirements are not met, then the results will be very terrible. So here's one example comparing ISD with the delta L or eigenvalue solution. And we can see that the ISD results give you a very nice smooth curve in both magnitude and phase angle. And or phase delay, you can say. And for the delta L or eigenvalue solution, you get a lot of spikes, right, in both magnitude and phase delay. So in ISD, you can click just one button to compare ISD results with eigenvalue. And then we can talk about in ISD, we also let you define impedance for non-uniform transmission line. After this embedding, short trace from a long trace, we get trace-only results. And then because the PCD trace is actually non-uniform transmission line, if we want to just use one number to express that, right, one impedance number to express that non-uniform transmission line, we can try to change the reference impedance until the return loss becomes minimum, and then we can say, aha, that's that reference impedance corresponds to that non-uniform transmission line, or the this impedance is the best number to represent that non-uniform transmission line's impedance. So all that is automated, and in ISD we can also do skewless de-embedding. Right? So very often we found that yeah, especially if you want to embed a short trace from a long trace, they actually have different skews, and if the skews are opposite to each other, the results can actually be worse. Right? And so by clicking the button, ISD lets you do that kind of skewless embedding. So here's one example. So the short trace has a positive skew, the long trace has negative skew, and if we don't deskew it before the embedding, then the results will actually be even worse skew. So here's one graph to show that with or without skew, the differential insertion loss after the embedding can actually be quite different, and ISD helps you do that deskew automatically. Now, in this case, the delta L or eigenvalue solution becomes very unstable. Again, we are trying to embed 2-inch trace from a 5-inch trace, right? And delta L solution becomes totally unusable. But ISD results are still nice and smooth. And how did we do it? And what is the reason, right? And turns out, in this case, the short trace was back-drilled, but long trace was not back-drilled. And so obviously it violates the one big assumption of delta L or eigenvalue solution. And because the long structures are not identical. And in ISD, we say, okay, we don't really care about short trace impedance. We just follow the long trace impedance to do that embedding. So the end results are nice and smooth without causality error. So now after we do this the embedding accurately, we can talk about Dkdf extraction. Right? And all that process is automated between short trace and long trace. We do the embedding and we get trace-only results, and then we fit all S parameters in insertion loss, return loss, next facts, and also TDR and TDT by a 2D solver. And after we fit so many terms, we can actually feel more confident about the Dkdf and roughness results we get. So here's one example. Yeah, we can use many different models to do that curve fitting, and the results will be slightly different. And this is explained in our paper published with Cisco. You can go to our website and look at one paper under publication. So we use the wideband Debye model, right, or Georgiavic-Sacker model, using 4 variables to express frequency-dependent Dk and Df over a wide frequency range. And we use the so-called effective conductivity model, right, to account for the surface roughness. And this is a more rigorous approach by solving Maxwell's equation numerically, and then we could derive the effective conductivity to account for the surface roughness. Now, if people want to use a Hooray model, you can certainly convert the effective conductivity model into a Hooray model again. Right? So all this is automated after you get these embedded results. You know, from ISD, you input them into our other software, ADK. You select a template, whether it's a strip line, microstrip, coplanar, and then you enter a few parameters, and then you click run, and it's going to automatically extract Dkdf and the roughness. So in this case, we match insertion loss, return loss, magnitude and phase. We match next and fixed, magnitude and phase. We match DDIL, differential insertion loss, differential return loss, magnitude and phase. And common mode insertion loss, return loss, again, magnitude and phase, even TDR and TDT. So after we match so many terms, right, as parameters, TDR, TDT, then yeah, we can feel more comfortable about the dk values we extract. And of course, the dk values will depend on the model you choose. Right? So here's a quick summary of the extracted dk and df, right? And then effective conductivity. And then after we got that model, we can now talk about S parameter for any length and yeah, to any frequency. So let's talk about PCIe 5.0 spec, because now it's gaining more and more interest. And yeah, we note that PCIe 5.0 spec actually defines the spec after the embedding, right? And then there's one interesting thing in PCIe 5.0, CCICN, right? Component contribution integrated crosstalk noise. And basically next and fast can be affected by impedance, especially next, right? They are affected by impedance. And so if you don't do the embedding correctly, then next and fast will be off. And in this case, if we talk about whether it can meet the CCICN spec, right? It's actually very close, and the spec is 250 microvolts, right? And in this case, we say, okay, it's 242 microvolts. So when they are so close, obviously, you know, the embedding becomes very critical. How you can have very accurate embedding to say this component passes the spec or not. Yeah, as a summary, we said accurate embedding is very crucial for design verification, compliance testing, and the Dkdf extraction. And a traditional method will give you a lot of errors, right? If the test fixture and calibration structure are different impedance, and ISD addresses such impedance variation through software instead of hardware, so it can help you improve the embedding accuracy and reduce hardware cost. So if you want to investigate more, you can look at our website and Facebook page. Right? We have posted a number of articles through Facebook. Now let me do a quick demo. So you open up In-Situ De-embedding GUI, ISD GUI. So as we said, the process is very simple. First, you bring in a 2x through coupon. In this case, let's bring in a 5-inch trace, right? And then the second step, you bring in a 7-inch trace, fixture plus DUT. And then the third step, you click Auto. It gives you a quick summary, like port sequence and delay and a skew, right? And how many points. And if you want to know more about the so-called causality metric and all that, you can go to SI Tools and check S parameter, causality, quality, etc. And automatically, it's going to set the port sequence for you after it identifies a port sequence. And if it shows up something, not what you thought it should be, then it's time to investigate the data. And then the fourth step is to click run. So in 95% of cases, you only have to go through this route, 1, 2, 3, 4, and that's it. Right? And so in some cases, if you want to compare with results without the impedance correction, you can turn off impedance correction by checking this box here. And in other cases, you may want to embed from two sides, left and right sides, one at a time, because the left sides and right sides are different. Then you can go through this pause to skip. The first time you skip the left side, the second time you skip the right side. So there are many options you can do, yeah, you can take care of the active device here also. And there are many menu buttons here you can choose to plot TDR, to plot S parameter, etc. So now that yeah, in this case it's done, right? It shows you the S parameters, single-ended S parameters, and you can close that. If you want to compare with the embedding results. Oh, sorry. Some people just say I was not sharing the GUI. Sorry about that. Okay. Yep. Yeah. Let me take a step back. Okay. So the first step, you bring in a 2x through like this. The second step, you bring in fixture plus DUT file. And then third step, you click auto, right? It shows you this port sequence and phase delay and the skew, etc. And then you click run, and we just ran it. It shows the results. And after we got the results, we can plot S parameter, DUT, for example, in differential mode. We can plot the embedding file, differential mode, for example, like this. And you can certainly compare the results with delta L just by clicking one button. So let me blow it up here. And so just by clicking one button, you can see that right, the delta L or eigenvalue solution is this blue curve here. It has this kind of a spikes, as we said in the PowerPoint slides. And the black curve, right, is the initial Isd results with reference impedance set to 100 ohm. And because this leftover trace is not really 100 ohm, it's closer to 90 ohms. So the program automatically identifies what's the best reference impedance to use. In this case, 89.56 ohm. And then it just re-reference it to that impedance. And it gives you this magenta curve. And it's nice and smooth like this, right? So when you want to talk about PCB trace attenuation, right, this obviously is a much more believable curve you can use, and instead of the curve that has a lot of spikes. And as we said, when you want to do Dkdf extraction, if you have so many spikes, then obviously that's going to give you problems too. So that's Isd demo. And for Dkdf extraction, you can go to ADK, click on this extract Dkdf. And you can bring in the embedding results, the DUT file, and this is 2-inch trace left over. And you can set certain parameters and select any template you want to use. And many times people just use a homogeneous stripline template, and then you click run, and it's going to automatically change the red numbers, right, into some new numbers. And yeah, these red numbers are going to be optimized. The black numbers are fixed numbers. So yeah, at this time, I'm going to open up the floor for Q&A. Let me unmute everybody. Let me see how I do that here. Okay, so I've unmuted everybody. So let me read one question from the chat box. Can you please discuss how to use scaling for lead-in flight time? Yeah, that's a good question. So here in Isd, as we say, in 95% of times, you probably just need to do 1, 2, 3, 4, and then you are done. And in some other cases, you can actually scale your lead-in flight times. Let's say sometimes you want to make it a little bit longer, 1.1 or 1.05, right? Sometimes you want to make it a little bit shorter, like 0.95. And the reason for doing that is to account for extra delay or extra structure after this 2x through, 1/2 or 2x through, or even before, slightly before 1/2 or 2x through. And so one application is like you have this 2x through trace for PCB only, but then you want to really embed the vias hanging at the end of that middle of 2x through up to a connector or package, right? And you don't want to prepare 2x through with the vias in the middle, and that's not the definition of a good 2x through either. And so in that case, you still go ahead and prepare 2x through with PCB, but then you just scale a little bit more, right? Like 5% more. You have to figure out how much more you want to embed. And then it will help you remove that vias, right? After the trace. Yeah. So that's what this scaling is useful. So any other question?
Yeah, and the question is forward. When you want to use a 2x through topology, how the fixture plus the dot, is there a minimum length delta that has to be observed?
In general, we want the 2x through to be a little bit shorter than the fixture itself, so that we don't end up embedding into the DUT. Right? So in general, we say, okay, if your DUT is a connector, a package, or whatever, you want to reserve probably 40 mils to 100 mils, right, away from the DUT. Because we know there's manufacturing variation and this and that. And so if you have this 40 mil to 100 mil margin, then after the embedding, we can be sure that the reference plane will still be on the PCB trace instead of inside the DUT. Right? If you want to avoid sometimes you embed a little bit too much into DUT, it's better that you prepare your 2x through trace a little bit shorter than your fixture itself.
No, my question is like when you show the eigenmode methodology where you have a 5-inch and a 7-inch, and then basically you're using the delta L method. In that scenario, you're still using a 2x through to de-embed, but there's have to be a, if it's 5 inches, does 5 inches and 5.5 inches work, or what is the minimum delta between the two lengths in order for you to be able to de-embed it correctly?
In general, we saw good results even for only like half an inch delta.
I see.
And I know that what is that called? There's one spec, right? D something 35D or something. And they have a specific length requirement, but for ISD, you don't really need that. Yeah, we are talking about like 2-inch, 5-inch, 10-inch, trays for one specific industry spec, yeah, and a PCB spec. But yeah, we don't have to observe this kind of requirement. It can be arbitrary.
And then as far as the 1x open and the 1x short, so 1x open, if you're talking about device on as device off, device on, we can de-embed, use the fixture to de-embed to the BGA pad, to de-embed to the C4, using the same concept with 1x open with the device, and then of course without the device 1x open, then put the device, and then you could use that 1x open fixture to de-embed all the way to the BGA or to the C4. Does that suffice?
Yeah, and that will work. The only thing you want to watch out for is if you just use 1x open, if you use 1x open only, then very often you may end up embedding into the DUT, right? So that's something you want to watch out for. Yeah. And the best is to do 1x open plus 1x short. And yeah, also try to reserve some distance away from the DUT. Yeah. Eventually, you want to really put your reference plane in a PCB or on the PCB trace. You want to avoid the situation, right? You embed into the DUT.
I see. So if I have a device 1x open without the device, and then the same thing, I could just create a plane, short everything, and create a 1x short, and then use a combination of a 1x open, 1x short to move my reference plane right to the, in this case, I'm mostly interested at the BGA pad or the C4 pad.
Right. Yeah, that will work out better if you have both 1x open and 1x short. And because the attenuation, insertion loss, plus the return loss information can be reconstructed more accurately, yeah, than just 1x open by itself.
And then the question is, in the Roide VNA, this software is you can build this software into the VNA, and then you can have the software standalone. Is there any delta between the software running in the VNA and the software running outside the VNA?
They are identical. Yeah. Of course,
Okay.
if you run it as a standalone mode, and there's probably more options you can choose from the menu bar and here and there. Yeah.
I see.
Hey, Dr. Huang, this is Michael.
Hi, Michael.
Hi, how are you? So I have a question about the 1x shorts. If the short has some offset delay, should we take it into the account or no? Doesn't matter.
Right. Of course, ideally, you like 1x short and 1x open to have the same delay. So this is a good question. In the past half a year, we have seen quite a few cases when people try to apply 1x open plus 1x short. The delays could be different because when they did the 1x short, they could end up shorting too much. And so there will be some delay difference. And ISD now can account for some of those delay difference automatically. So it's not a major problem, but of course, you don't want to have two structures, 1x open and 1x short, have different delay, to like 50 picosecond, 100 picosecond, right? So yeah, and eventually, yeah, ISD cannot correct that either. Yeah. Just make sure that even if you have some delay difference, it's not too big. Yeah. Less than 20, 30 picosecond difference, that can be adjusted nicely, yeah, automatically.
Hi, Professor. I have a question. When you are doing the 1x a 1x open use case, where we imagine where you have a differential signal, 1x open that you are trying to measure, can you just extract your 1x open information, let's say from your PN, and reuse that to de-embed also the end side? And just assuming that if you have the same reference plane at the beginning when you were calibrating both ports, just you can use the same file on the P and the N. Will that make any difference on your de-embedding result?
I assume your question is about how we can reconstruct 1x through from 1x open. Is that what your question is?
No, the question is more about if when you are doing the 1x open of a differential network where you have two ports, and then you have the two ports of your VNA connected to your differential structure, and you measure the 1x open from, let's say, the PN of your structure, and then you reuse that 1x open information on the end side of your structure. Is that feasible?
So you have a differential structure, P and N, and then you only measure one either
leg.
One leg, yeah.
One leg, and then you want to apply it to the other leg. Well, if you have loose coupling, it's possible. Otherwise, it's better that you do two-port, 1x open measurements, right? From two-port 1x open, you can reconstruct a four-port to 1x through. Right? For one port 1x open, you can reconstruct a two-port 1x through. And then if the P size and N size are loosely coupled, yeah, you can possibly just use one port 1x open to derive for both. Yeah.
Okay. So yeah, but what you're saying, the best use case is to actually do to measure the 1x open of the two port. That's the best use case. But and you also mentioned recently that you had the tool was integrated with the Rodenschwarz VNA. So what we found is that the current integration that we had on the VNA, it just allowed you to do when you're performing a 1x open, you can just measure it from one port, and the assumption being that by just measuring the 1x open, let's say of your P legs, you can reuse it on your N legs when you're doing the de-embedding, just because the tool is looking for the reference plane. It doesn't really matter if you choose the P and the N. And I was just trying to get your feedback about it, because I will expect there will be some a slight difference on your result if you were to go that way, because if we consider a scenario where your P legs and your N legs, we have some skew, they don't have the same length. I don't think it's a fair assumption to reuse the same 1x open file for both.
Right. If P and N have a very large skew, they have very actually that would not be really P and N anymore. And in that case, you want to do each one of them separately. Yeah. And if it's a differential structure, normally we said the skew is not really that large, right? Maybe 1 picosecond, probably no more than 10 picosecond. That would be, unless this is a very large structure. And yeah, so for Rodi and Schwarz VNA use case, yeah, I guess you can talk to Rodi and Schwarz, or you can always save your files, right, separately, and then import them into ISD, right? And then for 1x open, for example, you can enter any number of ports, right? 2 ports, 3 ports, 4 ports, doesn't matter. And then it's going to reconstruct one X through in 2 times the number of ports you entered.
Okay, I see. Okay, thanks. Last little question. What's the active dot? When do we need to use it and have it? By default, it's usually disabled. In what use case scenario do you recommend we should enable it? Just
Obviously, when the device under test is an active device, and many people do use that, especially for the chip manufacturers. And otherwise, the program is going to assume positive structure all the way. And so if you have gains, right, more than 0 dB insertion or return loss, whatever, in your device, then it's better that you turn on this active DOT. And also there are some other use cases like circulator. For circulator, it's not necessarily active, but you want to turn off enforced passivity. When we have this enforced passivity button turned on, it also enforces reciprocity, and for circulator, it's not reciprocal, so you want to turn off. This is just another thing we want to talk about. So let me look at the chat box. There's one question.
Okay,
when
thank you.
Using a differential line for Dkdf roughness extraction, is the line impedance required to be 50 ohm, or is it arbitrary? Yeah, of course. The trace impedance can be arbitrary, and that's exactly one example we showed in the PowerPoint slides too. That example has differential impedance close to 90 ohms. So yeah, the trace impedance doesn't have to be 100 ohm differential. And then there's another question through the chat box. When I use a 2x through with different PCB material, what are the requirements? Should the 2x through and fixture have the same length of electricity? So in general, when we prepare a 2x through coupon, we like them to be on the same board, right? And if 2x through is from different board, different material, at least you want to make sure that the delay and attenuation are close, right? Otherwise, even if we can correct impedance, the delay and attenuation information will be from that 2x through, right? So if it's going to be from a different board with different material, then yeah, that's something you want to watch out for. If it's so different, you might as well just use a simulation model for 2x through. We actually got pretty good results using simulation 2x through and simulated 2x through model to do this kind of embedding.
Can you talk about the crosstalk? I think in your early agenda, you listed that you can de-embed crosstalk. Can you elaborate?
Right. Yeah, it's a good question. Let me bring this one here. So in this example, we apparently have only one trace as 2x through. And in general, there's a, right, the lines are getting closer and closer to each other when they get to DUT. And so there will be some crosstalk here. And if you don't have 2 times or 2x, if you don't have a differential pair for 2x through, if you just use one line, right? That's what happened in many cases. Then we can also embed crosstalk, especially for near-end crosstalk. Right? The reason is we followed the differential impedance for the fixture. And we know the differential impedance is related to differential return loss, SDD11. And SDD11 is equal to 1/2 of S11 plus S22 minus 2 times S12. And if we match S11 single-ended, right, return loss, if we match S22, another single-ended return loss, and then we match SDD11, differential return loss, or impedance, whichever you call it. And then automatically we can get S12, that near-end crosstalk very nicely. Right? So for near-end crosstalk, we can use one single trace to embed very, very well. For far-end crosstalk, then we can do some estimates. That estimate is usually better if the fixed is a little bit larger, right? Let's say larger than minus 40 dB or even minus 30 dB. Then that kind of estimate will be more accurate. If the fixed turns out to be very small, like in a straight line case, fixed is typically very small, but next can sometimes be large, then you don't want to do that kind of fixed estimate. You will just assume fixed is equal to 0 in a fixture. And all that is automated in ISD also. By default, if you enter a 2-port 2x through, especially in this case, mezzanine connector 2x through in 2 ports, but your total structure is in 4 ports. And by default, it's going to do all that, near-end crosstalk, the embedding, etc. But no fine crosstalk the embedding. And if you select another button, like here, if you want to match fixture impedance, if you select differential plus SE only, then it's going to estimate that fine crosstalk for you also. But by default, it's not going to do that. It's going to assume the fine crosstalk for the fixture is 0 if your 2x through, actually 2x through is in 2 port, but your fixture plus DUT is in 4 ports or more. Right? So it's explained in the user guide. So there are many ways you can do this. Yeah.
Pcie, it's Paul. Can you hear me?
Yeah, I can hear you.
Yes. Regarding the 2x through, if it is very short, what is the disadvantage? Let's say if it's ½ an inch short.
Half an inch is not necessarily a problem. It's all relative. We are talking about electrical length, right? Because fundamentally ISD is based on FFT, and in order to have enough resolution, we need to have enough bandwidth. And ideally, let's say at the highest frequency, we should see at least 3 wavelengths, right? So at the highest frequency, 2x through should have gone through, let's say, 360 degrees times 3, right? That kind of phase angle change. And if it's very short, then you can actually go through this very simple one, run special small fixture. And yeah, if somehow it's less than, let's say, a quarter wavelength at the highest frequency, right? Then it will just do the square root of ABCD matrix, and then just use that kind of a simple embedding, and it will work out nicely for very, very small structure. Right? In general, yeah, we like to have at least like 3 wavelengths at the highest frequency. Right? So for half an inch structure, 2x through, if you can measure it to 40, 50 gigahertz, then yeah, that's more than enough.
Mm-hmm. Okay, thank you.
Thank you. Let me look at another one here. How can I embed SP2T single pole 2-throw DUT with 2x through when it's measured with S3P, assuming we have identical lines at the input and output of DUT? There are X-inch lines at the input and X-inch lines at the output. Yeah, it's a very good question. Actually, it's explained in our user guide. And in our user guide, if you click help, there's a user guide. There's a 3-port example, and that's actually even more complicated. Right, this is a 3-port structure. And on the left side is 1 line coming in. On the right side is 2 lines going out. And these 3 lines are not even the same. And for your case, it's a 3-port structure. You can go ahead and do the 2x through and then bring in a S3P file, for example, like this. And then you are going to assign all ports on the left side. And there are many ways you can go about this. You can, if they are all loosely coupled or no coupling, right? You can just say match fixture impedance single-ended only and click run, and that's it, right? If your input is something in S2P file. If you have a 2x through in S2P, and assuming that all ports, all lead-ins or lead-outs are very similar, have similar lengths and delay, and you can use 2x through. You can just do this, and then if there's no coupling, you select this button. As we said, in special cases, you can select some of these options and then click run, and that's it. And if you have coupling among all of them, all these 3 lines, lead-ins, lead-out, you just set it to default and then click run. And then if somehow 2 lines are coupled and 1 line is not coupled, then you can do it in 2 steps. The first step, you say, okay, I want to skip the embedding port 1 and go ahead and embed only port 2 and 3, click run. The second step, you bring in the DUT file from the first step. Right? And it will be in this form, and DUT S3P. And then you say, okay, the next time around, you want to skip port 2 and 3. And then you click run. And then your DUT file will be in test3p, DUT S3P, DUT S3P. So you can do it in 2 steps. So there are many ways you can go about this, depending on whether your lines are coupled or not. Right? So any other question? I know we have run over time by more than 15 minutes. There's no other question. We can call it for today. No other question? Okay, great. Okay, there's one. What's about the embedding? What's about the embedding with some AC coupling in the line? Yeah, AC coupling is not recommended because for 2x through, we really assume there's a DC through. So for AC coupling, unless it's at very low frequency, you can just cut it off. You don't want to see that sharp drop of insertion loss, less than 100 megahertz or something. But if your insertion loss drop is below 10 megahertz, you can just cut off that piece, and then you run ISD as is. Basically, we don't want to see a sharp drop in insertion loss or 2x through at the low frequency. 2x through means DC through. So I guess that's it for today. Thank you so much.